Hello, statics enthusiasts. Today we're going to be talking about equilibrium of a particle and what's perhaps the most important takeaway from your entire statics class and maybe your entire academic career. And that is how to draw a proper free body diagram. I was once talking to a manager at Boeing and I asked, how are the graduates coming from university? Do they know how to do their job? And she said, yeah, some of them. But some can't even draw a decent free body diagram. She equated being ready for an engineering job at Boeing with being able to draw a proper free body diagram. So let's jump into this and get started. And to do that, we're going to talk about Newton's first law of motion. Now this is a law of motion, and we know in statics we're not moving, but we'll have a special application of that law of motion. So what is Newton's first law? Newton's first law says an object at rest will stay at rest, an object in motion will stay in motion unless acted upon by a net external force. It's also known as the law of inertia. In statics, we're looking at equilibrium, where each point on an object has the same constant velocity. If we put those two things together, it's basically saying that our object has no acceleration because it has same constant velocity. Newton's second law states the sum of the forces acting on a body is going to be equal to mass times acceleration. If the acceleration is 0, as it is in equilibrium, then we have the equation sum of the forces is equal to 0. This equation here is the sum of all net forces acting on an object. So if we look back at Newton's first law, that means that an object at rest will stay at rest, or an object in motion will stay at motion. So we're not necessarily just looking at objects that are not moving. We're looking at objects that are not accelerating. So an object could either be at rest or going at a constant speed. There's one other word here that we're throwing around that I wanted to define very succinctly, and that's particle. Why are we talking about equilibrium of a particle? Well, the reason is we kind of want to ease ourselves in. We're making a simplification to reality so that we can learn equilibrium and learn free body diagrams. That simplification is we're going to take an object and model it as if all of its mass existed at its mass center. A more simple way to put that is we're going to have objects that have mass but no shape. We're treating them like a dot, a little particle. But they still have mass. They'd have to have mass. So we're going to have that simplification just for one chapter, so don't get too used to it. And after that, we're going to go to rigid body equilibrium, where we're going to have to look at torques and moments. A torque and a moment are the same thing. We're going to bring those in, and it'll allow us to continue our study of equilibrium. So let's jump right into some free body diagrams. I have 3 simple steps here for drawing a free body diagram. First, you draw an outline of your object. This is very important because, as I said, next chapter we're going to start bringing in moments and torques. And you have to have an object and the size of the object in order to calculate those correctly. So no more free body diagrams with just a dot, unless that's where the forces are acting, if they're acting on a little small piece. One of the most important parts of a free body diagram is choosing the proper body. What am I analyzing? And we're going to take a little snippet out of the system that we're analyzing and draw a free body diagram. Every body will have its own free body diagram. And sometimes you'll even combine bodies to make a free body diagram of multiple bodies together. The body that you choose dictates the forces that you're going to put on it. As you can see here, after we draw an outline of the object, you're going to trace the object with your hand and add all the forces acting on that body. So whichever body you choose, we're only drawing the forces on that body, not on the bodies next to it. And then we're going to label each force. So for this problem, we have some ropes, and we might want to figure out what the forces in those ropes are. I could draw a free body diagram of the crate, and that would give me the tension in one rope. But we probably want to know the tension in multiple ropes. I'm going to choose the ring there as the body that I want to draw. So if I have that as my body, I'm going to draw the ring first. I draw the outline of my shape. And then I always recommend tracing it with your finger. Go along as you look at the picture and say, oh, there's something pulling on it here. I better make a force. And then you always want to label it. I'm going to call that FAC. Okay. And I'm going to trace and keep going, and oh, there's one over here. I got to put one there too. I'm going to call that FAB. I'm going to keep going. I've got another one down here. I'm going to call that FAD. Any other forces acting on this ring? Probably weight. Now this problem, the weight's probably not going to be super important, but let's put it on there until we know otherwise. Okay, the weight of that ring, I'm going to put on there as well. Okay, a couple things to note here. First off, a free body diagram has to be free. What that means is we're going to choose our body and we're going to remove everything that's attached to it. It would not be a proper free body diagram if I still had the ropes attached to the ring. I have to remove the ropes and replace them with forces. Otherwise, the body is not free. Same thing with supports. The supports are removed and they are replaced with forces. The other thing to note is to make sure that you're only drawing the forces that are acting on that particular body. For example, if I drew another free body diagram of the crate, I'm going to draw an outline of my body, and then I draw the forces acting on it. Well, there'd be a force pulling up that I could call FAD. Notice how those are in two different directions. How can I have the same force in two different directions? Well, FAD on top here is pulling down on the ring, but it's pulling up on the crate. Okay? So these two forces, this one is what acts on the ring and this is what acts on the crate, and you could picture, if you put those two together, how they would cancel each other out. So it's really important to look at just the forces on the object that you drew. And it's also important to label each force. This is where our variables are going to come from when we do our equations of equilibrium. Spend time on your free body diagrams. For example, this one could be drawn in two different ways. I have to look really closely. You notice I have FAB and FAD. I have two different variables for the tensions. I need to look at that ring carefully. Does it look like the rope would slide through the ring? Does it look like this rope is attached to that rope and maybe they would have the same tension? If I look really closely, it's not. They're two separate ropes and therefore they'd have two separate tensions. Okay, so we have one free body diagram. Let's talk about some general items we might see. Okay, springs. We have a lot of springs in statics, and when you're analyzing a spring, you have to remember Hooke's law. You should be excited when you see a spring, because a lot of times it will allow you to put the magnitude of a force down. How would we know the force? Because we know Hooke's law. What does Hooke's law tell us? It tells us that the force in a spring is going to be equal to the spring constant times the change in length of the spring. It's important that you understand that that delta S is the change in length from the unstretched length. So you first have to determine what is the unstretched length of my spring, and then what is the current geometry of my spring. You take that current geometry, you subtract the original geometry, and that's how you get your delta S, multiply it by K, and we now have a force of one of those unknowns in our free body diagram. It can be super helpful in solving problems. Ropes. Now you just saw in the last one, I had quite a few ropes, and for each one of those I had an arrow that was pulling in the direction of a rope. Okay, this might sound obvious, but ropes cannot push. Okay, so make sure that your equations that you make out of your free body diagrams don't have the rope pushing. If you picture me throwing you the end of a rope, you grab onto it and I pull, I can transmit force if I pull in tension, but if I push, it does nothing, right? So that means that a rope always has to be pulling. What is pulling? Well, it looks like an arrow pulling away from that rope. This would be a rope in tension. Okay, make sure that your arrows are the right direction for ropes. Pulleys. As I showed in the last one, I had two separate tensions in the rope because those ropes were tied to the ring. They weren't sliding through it. In the case of pulleys, oftentimes, we will have a pulley and a rope going around it. Now, if that rope is in tension, which it has to be because it's a rope, then those two tensions are going to be the same. Why? Because if they weren't, the pulley would just rotate. If this T down here was greater than that T, the pulley would spin and they'd make themselves even. So pulleys can help us to determine the tension in a rope. It's one unknown instead of two. Finally, surface contact. You've probably learned about normal force. It's the same concept. If we have surface contact, let's say we have a wheel rolling down a ramp. If we want to draw the free body diagram of that wheel, it's going to have a force acting perpendicular to the ramp. Notice how I removed the ramp, made the body free, and put the force on it. And perhaps I'd have a weight pushing down as well. Okay, let's do a couple more free body diagrams. Okay, here we have a large tank being held up by a pulley. How is this one different? Well, the first thing is this is drawn in 3D, and when you first look at the object, it might look fairly complicated. Ask yourself, is there a way I can simplify the drawing? We have to first choose our body. If we're looking for the tension in these ropes, again, the body that we probably want to choose is the dot in the middle there, the pulley at O. If I choose to draw that pulley, I'm going to go ahead and draw it, draw an outline of my body. And then I notice there's a chain. A chain can only pull, so it has to have an arrow pointing up. Now here's where the pulley comes into play. I am going to draw two ropes, one here and one here. But because there's a pulley there, both of those are going to be the same. So I'm going to call this T, I'm going to call this T, and then the top one is already labeled as F. Okay? The free body diagram and the diagram are not the same thing. You should have a diagram of the problem on your paper as well as a free body diagram, and they should not be on top of each other. The free body diagram, the body has to be free. We've taken the chains away. And you notice that there's still geometry on the diagram that is very important to our drawing. Okay? We'd have to know what is the length here, what is that length in order to find the angle for when we draw our equations of motion. And of course, I'd want to draw the weight here as well, unless I was told that I was either told that it was light and it doesn't affect the problem, or there's no weight given, then we can assume the weight of the pulley is not important. Okay, let's do one more quick example. I have a few blocks and a spring in between them, and they're rolling down or they're sliding down a surface. Depending on what the question asks, you will be choosing the body to use for your free body diagram. In some cases, you may draw both of these bodies together with the spring, and that would be your body, all three combined. You would do that if you were trying to find how fast they move together. If you're trying to find the force in the spring, you're going to have to draw them separate. Otherwise, that force would not show up. Let me give you an example. If I were to draw them all together, very nice spring there. I would draw A and B. Okay. And now I'm going to take the surface away and replace it with forces. That would be a normal force on B. There would be a normal force on A, perpendicular to those surfaces. There would be a weight coming down on B, on A, and a weight on B. Okay. And we'd also have friction. If those are sliding down, the friction is going to oppose force. And I'm going to put the friction on A here. And I'm going to put the friction on B. Okay. That's a free body diagram where I chose both of these as a system for my body. Now, some of you might be seeing this as a little different than what you learned in physics. Maybe you're tempted to take this friction and move it up to the center and treat it as if it's acting in that mass center. That would work for the particle assumption we're in right now. But I encourage you to start drawing the full body and keep the forces where they act. Because in the very next chapter, we're going to be dealing with moments, and where the force acts is very important. Okay? You notice with this free body diagram, where I have the entire system, there's no spring force. Why? Because that would be internal to the body that I chose. The body is A, B, and the spring all together. And I only draw the forces acting on that body. If I needed to find the spring force, I'd have to draw a free body diagram of A. It would have some of the same forces. but it would also have the spring force pushing down on it. And then I could draw a free body diagram of B as well. Notice a few things here. Notice that when I drew the free body diagram of A and B, the spring force is in opposite directions, right? As B pushes down on A, that force is going to be pushing back on B, and it's going to be pushing down on A. Every action has an equal and opposite reaction. That's Newton's third law. Hopefully you can also picture that if I squish these back together, that's this free body diagram up here. That spring force cancels out that spring force. In every free body diagram, we're only drawing the forces acting on that body. Okay. Hopefully that gave you a quick introduction to free body diagrams. Keep in mind that your knowledge of free body diagrams and how to draw them correctly will continue to grow. As we get into more complicated problems, there's going to be more bodies that interact with each other. So ask questions, practice, and spend time on those free body diagrams. Next, I'd like to talk about equations of equilibrium. Equations of equilibrium come from Newton's second law. Sum of the forces is equal to mass times acceleration. And as we already said on the first slide, in statics, that acceleration is always 0. So we have sum of the forces as a vector is equal to 0. And I'm going to do something a little strange here and put a vector sign over that 0. Now that's not proper notation. You don't have to do that. I'm just showing you, I want to remind you that this is actually 3 zeros. This is 0i plus 0j plus 0k. And this force vector can be expanded as well. The sum of the forces in the x direction times I. Notice this is no longer a vector but a scalar. I'm separating out the directions I, j, and k. Sum of the forces in the y times j plus the sum of the forces in the z times k is going to be equal to 0i plus 0j plus 0k. Got to fix my misplaced harpoon up here so that we have everything correct. So this one equation, one vector equation, sum of the forces equals 0, is actually going to give us 3 scalar equations. And that's what we call our equations of equilibrium. The way that I like to break it out is you can either write it as a full vector equation here, or you can break out your directions and your scalars. How do you do that? Well, once you have your coordinate system drawn, you can just say in this direction, that's my x, I have sum of the forces in the x equals 0. In this direction, sum of the forces in the y equals 0. And then z, when we get to 3D, I'm just going to put a dot here. It'll depend on how you have your coordinate system, which directions you're drawing here. We'll have sum of the forces in the z are equal to 0. We now have our equations of equilibrium. These are 3 equations, so we're going to be able to solve for 3 unknowns simultaneously. And I'll be posting another video on some methods to do that. So that should give you an introduction to free body diagrams, equilibrium of a particle, and equations of equilibrium. Please let me know if you have any questions.